Hello. This time we're going to be looking at equivalent networks and how all the techniques we learnt about for Thevenin and Norton equivalents can be used with AC circuits as well. This is the first example we'll be looking at. It's a two-terminal network and it's linear, so it will have a Thevenin equivalent. We're asked to work out what that Thevenin equivalent is. Well, we start off exactly as if it was a DC circuit. The Thevenin equivalent voltage will be the open circuit voltage, so the voltage between A and B when there is nothing connected to those two terminals. We can work out what that is just by using the potential divider equation, because what we've got here is a potential divider. So, the open circuit voltage, or rather the phasor representation of the open circuit voltage, since we're working in terms of the phasor representations, is going to be the phasor representation of the voltage at this point here, which is just 4 millivolts at 90 degrees, multiplied by the impedance of this component. I'll just leave this as j omega L for now, divided by the total impedance in this potential divider, which is j omega L plus 1 over j omega C. And we need to work out what that is at a frequency of 50 kilohertz. Not forgetting to convert that 50 kilohertz into a radians per second frequency. That would just involve evaluating 4 milli at 90 degrees, which I could have just written as j times 4 milli, multiplied by j times 2 pi 50k times the inductance, which is just 1, divided by j times 2 pi 50k times 1 plus 1 over j times 2 times 50k times the capacitance in farads, which is just 68 picofarads. And now it's over to the calculator again. 4 milli at 90 degrees times j times 2 times pi times 50k divided by j times 2 times pi times 50k plus 1 divided by j times 2 times pi times 50k times 68 picofarads. And the result is 4.7 millivolts at a phase angle of 90 degrees. So, that's the phasor representation of the Thevenin equivalent voltage, or the voltage source in my Thevenin equivalent model. What about the impedance in the Thevenin model? Well, to do that, I just set all of the independent sources to 0. That involves setting this voltage source to 0, which means just replacing it with a wire. And I would end up with a impedance of the capacitor and the inductor in parallel. Well, the impedance of two things in parallel, Z1 times Z2 over Z1 plus Z2, standard formula for two impedances in parallel, still applies here with complex impedances. So that's just j omega L times 1 over j omega C all over j omega L plus 1 over j omega C. Multiply top and bottom of this by j omega C, and we end up with j omega L over 1 plus j squared omega squared LC. J squared is just minus 1, so that is j omega L over 1 minus omega squared LC. Time to go back to the calculator. J times 2 times pi times 50k times the inductance, 1, divided by 1 minus 2, well, I'll do it 4 times pi squared times L1 times C, 68 picofarads. And that just gives me, oops, I've forgotten the 50k. That would have been bad. There's a 50k squared in here as well. And that is 5.5 times 10 to the power of minus 10 to the power of 4 at a phase angle of minus 90 degrees. So that's my Thevenin equivalent impedance. Now, I could represent that as a capacitance, since it has a phase angle of minus 90 degrees. On an argon diagram, it's going to be down here. That's where capacitors are. If I wrote that as 5.5 times 10 to the power of 4 times minus j, I could equate that to minus j over omega c and work out that c, in this case, running out of paper, would be given by 1 over 5.5 times 10 to the power of 4 times omega. And if we plop that into the calculator, 2 times pi times 50k times 5.5 times 10 to the power of 4. Answer, about 5.788 times 10 to the power of minus 11, which almost everybody would write as 57.88 picofarads. So I could draw out my Thevenin equivalent network in terms of a 4.7 milli at 90 degrees voltage source in series with a 57.88 picofarad capacitor. And that network would behave exactly the same as this network, no matter what you add between those two terminals A and B. Although do note that this is only an equivalent network at the frequency of 50 kHz. If I change the frequency, the equivalent network would change as well. I can check if I've got this right by asking the simulator. The simulator cannot work out what the equivalent impedance is, but it can work out both the open circuit voltage and the closed circuit current. And I can predict what the closed circuit current must be from the values that I have worked out. The closed circuit current, or the phasor representation of it, should be the open circuit voltage divided by the impedance of this component here, which we already know. We worked it out here to be 5.5 times 10 to the power of 4 at minus 90 degrees. So our short circuit current should be the Thevenin voltage, or the open circuit voltage, divided by the Thevenin impedance, which is 4.7 milli at 90 degrees, divided by 5.5 times 10 to the power of 4 at minus 90 degrees. And that is equal to 4.7 milli at 90 divided by 5.5 e to the 4 at minus 90, or about 8.546 times 10 to the power of minus 8, which I will write as 85.46 nanoamps at 180 degrees. So if I've got my impedance correct, that should be the short circuit current. Let's try it. Here I've built the circuit and I'm measuring the open circuit voltage, and that is the 4.7 millivolts at 90 degrees that I was expecting. If I close the switch, then I'll be measuring the short circuit current through this ammeter. And within the limits of accuracy that I've been working to, yes, that is equal to the value that I was expecting. So good. I'm confident I've got this one right. You might also come across questions like this, in which you're given the Thevenin equivalent voltage, or the phasor representation of it, and some of the performance of the network, and asked what the Thevenin equivalent impedance is. And in this case, you can just use the known model of a Thevenin equivalent, which is a voltage source in series with an impedance. Construct the circuit using that Thevenin equivalent. That's a 10 millihenry. And note that this is a potential divider. This is 1 volt at minus 90 degrees, so it's just a sine wave. And we know the voltage across that inductor, and we know what the frequency is, so we can just apply the potential divider formula. 415.8 milli at minus 62.1 degrees is going to be equal to the voltage at that point there. Phasor representation is 1 volt at minus 90 degrees. That's just minus J, times the impedance of this inductor here. I'll just write it as J omega L for now, divided by the total impedance in the circuit, which is the unknown impedance due to the Thevenin model, plus J omega L. And rearrange this, we get ZTH plus J omega L is equal to minus J times J is just 1, because that would be minus J squared, and minus J squared is 1. So that's just omega L divided by 415.8 milli at minus 62.1 degrees. And then if I just subtract J omega L from both sides of this equation, I'll end up with a nice equation. The unknown impedance equals something. So then, back to the calculator. Not forgetting to change the frequency into radians per second, multiplied by the inductance, 10 milli, divided by 415.8 milli at minus 62.1 degrees, and then subtract J times 2 times pi times 10 kilohertz, that's omega, times the inductance in henries, that's 10 milli, and that should give me, oops, yeah, the Thevenin equivalent resistance. And in this case, the answer is 1K at 45 degrees. When you get a nice round answer like that, you can be pretty confident that you've got it right, at least in tutorial problems and exams. That's all for this one. Next time, we're going to go back and revisit a circuit that I looked at a long time ago.